Continuing physical chemistry, now we're starting chapter 5 and section 1. In chapter 5 we're going to talk about thermochemistry. Section 1 we're going to talk about the standard thermodynamic functions of reactions. Now first of all we divide into the condensed phases and the gaseous phase. In the condensed phases, which is solids and liquids, the standard state of course is a pure substance. Our pressure is denoted as 1 bar, which is 750 torr or 0.987 atm. Now be careful when you're looking up stuff in books, tables, on the internet, etc., because it used to be 1 atm, which is slightly different from 1 bar. So the numbers won't come out exactly the same. So make sure when you look up information, you know what you found. 1 bar, of course, the reason we do that is because that's with our SI units. The temperature can be anything. The standard state does not imply a specific temperature. It can be 10 kelvins, 1,000 kelvins, whatever you're interested in. Tables, of course, they try to be consistent, so usually they'll have something like 25 degrees Celsius, because that's roughly room temperature. So as an example, let's say we have Vm 200 knot. So this would be the volume, molar, that's what the M means. The knot means at 1 bar, and 200 implies 200 kelvins. Notice we don't bother to put the K for kelvins after the 200. Now for the gaseous state, there too is a standard state for that. Again, it's a pure substance, the same pressure, 1 bar, just like for the condensed phases. We're going to assume a perfect or ideal gas. Remember, we proved before that all ideal gases are perfect. And again, it's no specific temperature. It's whatever temperature you're interested in. Physical chemistry, chapter 5. We're doing section 2 now. Remember from before, we learned that nu I is greater than 0 for all products, and nu I is less than 0 for all reactants. So if we have a equation like this, benzene plus oxygen going to carbon dioxide and water, then what we're going to do is we're going to get a change in enthalpy. Notice the delta, so we're changing it. Is that an F? Should be trend. Oh, a temperature, not. Okay. So remember, the knot means 1 bar. That's our standard state for any phase. So again, we're writing it just like we had before. We have the 12. So we're doing the products first. So we're adding the 12, the enthalpy molar at temperature for the carbon dioxide at 1 bar, plus the enthalpy molar temperature of water at 1 bar. That's the knot. And then we're going to subtract out the reactants. Minus 2. Enthalpy molar at temperature of benzene, knot, meaning 1 bar, minus 15 times the enthalpy molar knot 1 bar at temperature for O2. Or another reaction, let's look at hydrogen. Notice the numbers here. So we have H2 gas plus O2 gas going to water, liquid. So we could have delta H naught 298 of minus 286 kilojoules per mole for the reaction as written. But if you do like in general chemistry, multiply by 2 to get rid of the fractions, then we have 2H2 gas plus O2 gas going to 2H2O liquid. It's the exact same reaction multiplied by 2. So then we get the change in enthalpy at 298 knot, meaning 1 bar, of minus 572, which is double that. That's kilojoules per mole for the reaction as written. So again, when you find any number, you have to know exactly what does it mean, what is it describing. Now, we don't actually have absolute enthalpies like written up here. Those absolute enthalpies simply are not available. So instead, what we're going to do is have a standard enthalpy of formation. So we're writing it like this. So, oops, there should be an H here. Delta H. Okay, so delta H formation, T, I, or F, T, I, not. So remember, the F means formation, because it's the enthalpy of formation. The T is at temperature, whatever temperature you're working with. So I is for your substance, like carbon dioxide, water, or whatever. And of course, the knot is your standard state, which is currently 1 bar. Continuing on physical chemistry, chapter 3, we're in chapter 5, we're in section 3 now. So we're talking about the standard enthalpy of formation, denoted delta F Ti naught. On the previous slide, we explained what all that means. So the definition, the enthalpy of formation of an element in its reference form is the most stable form of that element at temperature T. So remember, this is for elements only. For example, delta H F298 of O2 gas naught is equal to 0. So remember, at 298 standard pressure, 1 bar, oxygen is diatomic and is a gas. So this is the standard state, or the standard form, where it's equal to 0. And setting it equal to 0 has been arbitrarily decided because, well, I mean, enthalpy is actually U plus PV, but until we get to quantum mechanics, we can't actually find like absolute U or anything. So instead of trying to find, absolute H, we just came up with this enthalpy of formation. So anyway, but what that means is then, at the same state, 298 kelvins and 1 bar, oxygen in its triatomic form, ozone gas, is not equal to 0. And likewise, just pure monatomic oxygen is also not equal to 0. Oops, that would be not equal to 0. Because, it's the diatomic state where oxygen at 298 Kelvin and 1 bar is most stable, the most common form. Likewise, let's think of carbon, graphite. So again, at 298 kelvins and 1 bar, carbon is going to be in this graphite form. So the enthalpy of formation for that is equal to 0. So that means then, diamond can't be equal to 0. And it turns out to be actually 1.897 kilojoules per mole. Now, as another example, let's talk about a compound, formaldehyde. It's minus 115.8 kilojoules per mole. Again, that's at 298 kelvins and 1 bar. Now, here's how it's formed. Now, this is how you can, the formaldehyde here, so you can form it from its reference elements like this. You have 2 hydrogens, so you have H2. You have 1 oxygen, so you'd write it as 1/2 O2. And the carbon, we'll assume, comes from graphite, because that's the standard form, the most stable form. So it's just 1 here. So this is how you show a compound being made from its reference elements. And as you can see, it's okay to have fractions in the stoichiometric coefficients. Now again, that's assuming that we were at 1 bar, because that's the standard pressure. And again, that's assuming we're at 298 kelvins. And of course, that means we're assuming that all these gases were behaving ideally. Now, another way to write that in a more as a summation form or a generic form, the change in enthalpy of transition for at temperature for a reaction at 1 bar is equal to the sum over substance i's of the delta H of formation at that temperature for every substance I in 1 bar. But in all these, we have to get these from the tables because they are found experimentally. Here's another example of reaction. So we're going to have benzene again. No, this isn't benzene. This is what? Ethane? Okay, so ethane plus oxygen going to carbon dioxide and water. So to find this, what we're going to do is we're going to find the change in enthalpy at 298.9. So we're going to take the stoichiometric coefficients and we're going to start with the products because those are positive. So we're going to have 2 times the enthalpy of formation, the carbon dioxide, in its gaseous form, because that's what's given, plus 3, because it's coefficient, times the enthalpy of formation of H2O. Again, that's just the gas, because that's what's given in the reaction. And then we're going to subtract out the reactants. So this is a 1. You can leave this out, but I just put it explicitly so you can see. So it's 1 times delta H, the enthalpy of formation of our ethane here. And then again, you can have fractions for these coefficients. So this will be 7/2 times the standard enthalpy of formation for O2. Now I explicitly left this in, but if you've been paying attention, you would know this one is equal to 0. So you could have left this out if you wanted to save some space, but I wanted to make sure that you didn't think I forgot it or something. So once you look all these up in the tables in the back of your book or the internet or whatever, this comes out to minus 1,427.8 kilojoules per mole. Now, if you look at all these coefficients, you might be thinking, moles of what? And it's not really like a mole of this gas or a mole of that gas. It's per mole as the reaction is written. So what this would mean is it would be for 1 mole of the ethane, or 7/2 moles of O2, or 2 moles of carbon dioxide, or 3 moles of H2O. So this is why when you're looking stuff up, you really have to know what you're looking at. You need to, know some chemistry and not just flip through a book and find a number. So like I said, that mole there is not per mole of substance, but per mole of reaction, whatever that means. Physical chemistry, chapter 5, we're now doing section 4. So we talked before about the enthalpy of formation, standard enthalpy of formation. How do we measure this? Well, there are different methods. For example, we could do calorimetry. Calorimetry could be done at constant pressure, like an open system and ambient pressure, or a constant volume isochoric system. That'd be like a bomb calorimeter. So for like a constant volume system, remember then delta U is equal to Q at constant volume. Q at constant volume is equal to N times the molar heat capacity at constant volume times the change in temperature. Or we could do it spectroscopically by looking at the bond energies in the molecules, products and reactants to compare. Or we can do it from the Gibbs free energy in the third law to calculate the long wave. Or we can find temperature volume of Kc, where Kc is an equilibrium constant. We'll get to that later, how to calculate and so on. So let's talk about the relationship between the standard enthalpy of formation, or standard enthalpy and standard internal energy for a reaction. And remember, the naught means 1 bar because that's our standard state. So we know from before that H equals U plus PV, so therefore H naught equals U naught plus P naught V naught. So the change in enthalpy naught is going to be the change in internal energy naught. P is constant because we know what it is, it's 1 bar, that's what the naught means. And then the delta V naught. So again, this is only a constant pressure, 1 bar, because it's standard state. We're going to assume it's a constant temperature and an ideal gas for these calculations. Since for an ideal gas then, for an ideal change in volume, we'll use PV equals nRT to substitute in. So we have the change in enthalpy naught equals the change in internal energy naught plus delta N of gas, so I'll get to that in a minute, times R times T. T is temperature, R is the gas constant, 8.314 joules per mole Kelvin. Now to find delta N gas, basically you're going to do products minus reactants. So you're going to have the sum of substance I of Ni for all the gaseous products minus the sum over I of Ni for all the gaseous reactants. If there are any condensed phase solids or liquids, you just ignore those for this calculation because they're roughly constant volume. So delta N, it's going to, even though we're calculating moles, change in moles, we're going to say it has no units. So it's actually like the change of the number of moles divided by moles cancel out. Physical chemistry, chapter 5, section 4. Now, we just talked about reactions that had the gaseous phase. What if they have only the condensed phases, solids or liquids? Well, then delta N of G is equal to 0. So the enthalpy at a standard enthalpy is going to be equal to the standard internal energy. Now, even for gases, though, the delta N G RT term is going to be smaller compared to the internal change in internal energy term. But you still want to throw it in there to get a good number. Okay, now remember from general chemistry, Hess's law says the overall reaction enthalpy is the sum of the reaction enthalpies of the individual reactions into which a reaction may be divided. That should be obvious because we know H is a state function. For example, let's say we're going from our reactants to our products. So we have enthalpy at state 1, enthalpy at state 2. It doesn't matter if we do it in one big reaction or if we manage to do one reaction and then another reaction and another reaction. As long as we start with the same reactants, end with the same products, we can calculate the same change in enthalpy. Continuing on physical chemistry, chapter 5, we're finishing up section 4 now. So as an example, we want to find the change in the enthalpy for formation for, what is that, ethane. Okay, so we're going to take the ethane and build it from its elements, carbon and hydrogen. Now remember that we want the most stable form. So for carbon, that's graphite, and for hydrogen, that's the diatomic gas. So we're going to calculate exactly what is the change in enthalpy for this reaction. So here's the reaction. Now we're given these reference reactions. For example, if we take this ethane plus oxygen and burn it, we'll get carbon dioxide and water, and there's a change in enthalpy for that reaction. Well, so if we take graphite and oxygen, make carbon dioxide, there's a change in enthalpy for that reaction. Or if we take hydrogen, burn it with oxygen, get water, there's a change in enthalpy for that reaction. So remember what we said before about Hess's law. All we have to do is take those with the right numbers and get them to add up to the reaction that we actually want. So it turns out if we take 2 times that middle reaction, then we'll take that 2 times the enthalpy that we were given. And likewise, if we take 3 times that last reaction, then we'll have to just take 3 times the enthalpy given. And likewise, if we take 2 times the first reaction, actually, well, the reverse of the reaction, really. So then the change in enthalpy will be, oh no, actually it's not even 2 times, it's the same value, never mind. Just make sure you pay attention to pluses and minuses. We were given it forward, so it was minus change in the minus enthalpy. We wrote it backwards, so the one we're using is a positive enthalpy. So if you add these together and simplify, you'll end up with what we wanted, so you know that this is the correct number that we're after. So the change in enthalpy for making ethane from its constituent elements is just minus 85.0 kilojoules per mole. And remember, that's per mole as written here, which also happens to be a mole of the gas we want. Continuing on physical chemistry, chapter 5, section 5. Now we're going to talk about the temperature dependence of reaction heat. Remember, reaction heat, it does not mean Q, that means delta H. So keep that in mind, more confusion for you. Okay, so what we're talking about is how delta H changes with temperature. So one, we know that the change in enthalpy for a reaction at standard pressure is equal to the sum of the stoichiometric coefficients and times the enthalpy molar for each substance I at standard state. So P is constant because it's at the standard state of 1 bar. And delta HI, not for this purposes, we're going to say we know that at T1, like 298 kelvins or something. We want to find delta H2, state 2, so a different temperature. So the first thing we're going to do is we're going to take the change in reaction, enthalpy of reaction, and find the derivative with respect to temperature. So here's our derivative, change in enthalpy of reaction naught with respect to temperature. And that's equal then to the derivative with respect to temperature of the sum of nu I enthalpy molar substance I at 1 bar. So that's going to be equal to the sum of nu I times the derivative of this H molar for substance I naught with respect to temperature. And now we know from before then that the derivative of molar enthalpy for substance I at 1 bar with respect to temperature, holding P constant obviously because it's 1 bar, is just equal to the molar heat capacity for substance I at constant pressure, which is kind of redundant because we said 1 bar, so you know what the pressure is. Okay, so the derivative of the enthalpy of reaction naught with respect to temperature then is equal to the sum over substance I of nu sub I of the molar heat capacity for substance I, holding pressure constant at 1 bar, which is just equal to the change into the molar heat capacity at 1 bar. So then we end up with dividing or multiplying by dt, so we get, no, not yet, never mind. Oh yeah, okay, good. So then we have, so multiplying by dt, so we get differentials on both sides. So we have the differential of the change in enthalpy of reaction naught over here is equal to the change in the heat capacity molar times the differential of temperature. Now we can integrate both sides with respect to temperature. So we have T1, the integral from temperature 1 to temperature 2 of the differential of the change of enthalpy of reaction at standard state is equal to the definite integral from temperature 1 to temperature 2 of the molar heat capacity at standard pressure with respect to temperature. Integrating that, then we get the change in enthalpy at standard pressure of temperature 2 minus the change in enthalpy at 1 bar at temperature 1 is just equal to the integral of the change in the heat capacity with respect to temperature. This whole equation is known as Kirchhoff's law, or Kirchhoff's law, I don't know how to pronounce that, but anyway. So just adding to get the delta H by itself, delta H naught at temperature 2 is just equal to delta H naught at temperature 1, for example, 298 Kelvin, plus the integral from 298 Kelvin or whatever initial temperature to T2 of delta Cp dt. And delta Cp is something that we can find in different tables. Physical chemistry, chapter 5. Now in section 7, we're talking about conventional entropies and the third law of thermodynamics. Now, conventional entropy is the same as relative entropy or absolute entropy. The second law, remember, lets us find changes in entropy, not absolute entropy. So what we're going to do is we're going to set up a reference state. Now this reference state will be slightly different than what we have from enthalpy, so listen carefully. Reference state for finding entropy is a pure element in its stable, liquid, or solid form in the limit as temperature approaches 0 kelvins. Now remember, there are no gases at 0 kelvins, so this part's different from when we did enthalpy, remember. Now 0 Kelvin is also unattainable. That's why we're actually using the limit as temperature approaches 0 instead of just saying that temperature is equal to 0. So what do we have then is the molar entropy at 0, that means temperature 0, not means 1 bar. So that's the limit as temperature approaches 0 of the entropy molar at temperature 1 bar, and that's equal to 0. And this was arbitrarily set. Now delta S, remember, is equal to delta S molar T2 naught minus S molar T1 naught. And we just said then that this one is equal to 0. But, of course, there'll be an entropy change on the way up to temperature 2. So we still have to take the integral from temperature 1 to temperature 2 of the heat capacity at constant pressure divided by temperature with respect to T. That's one term. Plus, we're going to add in the entropy of any transitions, like from melting or boiling or whatever, any other phase transitions. Now, let's talk about the absolute entropy then at absolute 0 kelvins is equal to 0. That's what we just said. And that's for any element or compound. Contrast that with what we just said about enthalpy, remember, where it's only elements that are equal to 0. So for example, water, the absolute entropy, molar at temperature 0 and 1 bar is going to be equal to 0. Or for the gas diatomic oxygen, the absolute entropy molar at 0 kelvins and 1 bar is going to be equal to 0. Either way. Now, we have a couple of different third law statements. One, the entropy of all pure, perfect, crystalline substances is the same at temperature equals 0. That's the Max Planck version. Physical chemistry, chapter 5, section 7. We're talking about the third law of thermodynamic statement. Now we've got another form of the statement. So as temperature approaches 0 kelvins, delta S for all reactions approaches 0. This is the Nernst-Simon statement. So here's an example. Here's a graph. On the y-axis, we sort of have an entropy. It's entropy molar at temperature minus entropy molar at 0, which is equal to 0. So it really is just molar entropy at our temperature of interest. And on the horizontal axis, we have temperature. So what we've done is graph sulfur. So not only is S for entropy, but S, of course, is still sulfur. And both of these are in the solid form, but it's got two different crystalline phases. We have the monoclinic and the rhombic. So what this is showing you, at any temperature, except for 0, we have the monoclinic has more entropy than the rhombic. But as the temperature approaches 0, they get closer and closer together. So presumably, if you could actually get to 0, they would be the same. So the more stable form has less entropy. In this case, rhombic form of sulfur. So the Nernst-Simon statement is only true, though, if the substance is at internal equilibrium, not in unstable form. For example, if you had a supercooled liquid, that's not an equilibrium state, so all this doesn't really apply. That's something totally different. Now remember back before when we did the Maxwell relations and the Gibbs equations, we said that thermodynamics wouldn't give us a way to calculate absolute entropy, but then we came up with the derivative of Gibbs free energy with respect to temperature holding pressure constant is equal to minus S. And I asked you the question, did we or did we not find a way to find absolute entropy? Well, apparently the answer is yes, here we are. So also, if we put in deltas for that, then we also have the derivative of the change in Gibbs free energy with respect to temperature holding pressure constant is equal to the change in entropy. We also have the change in entropy is going to be the entropy at temperature 2 minus the initial entropy, which we've arbitrarily set to 0. Well, not exactly arbitrarily, but we set that to 0. So that's just the entropy at our temperature of interest. So that's going to be equal to the integral from 0 to temperature 2 of our heat capacity constant pressure divided by temperature with respect to temperature. And we also know from our Maxwell relations or our Gibbs equations that the derivative of entropy with respect to temperature holding pressure constant is equal to Cp over T. Okay, we're continuing physical chemistry, chapter 5, section 7. So we're finding the the absolute entropy of substance. So let's say we have a liquid and we want to find the absolute entropy. Then, well, what we have is the entropy of the molar of the temperature 2 naught is going to be equal to the entropy from 0 to the temperature of fusion, that's the melting point, of the heat capacity of the solid form divided by temperature with respect to temperature. Plus, we're going to add in the change in enthalpy of fusion at standard state divided by temperature of fusion. And then we're going to have another integral from the temperature of fusion to temperature 2, our temperature of interest. And that's of the molar heat capacity of the liquid divided by temperature with respect to temperature. Now, we have an obvious problem though. Since we can't actually start at temperature equals 0, we don't have a heat capacity for the substance at temperature equal to 0. That's impossible. So Debye's theory is going to fill that in for us. Now, if Debye sounds familiar, remember that's also the unit of the dipole moment. Now, this is actually from statistical mechanics, and this is called Debye extrapolation, because he's extrapolating a trend all the way down to 0, absolute 0. So what Debye said was two things. One is that the molar heat capacity at constant pressure, naught, is roughly equal to the molar heat capacity at constant volume, but also at pressure, naught. And that's roughly equal to A T cubed for nonmetals only. Now this is T for temperature, and A is a constant, this characteristic of the substance. But this only applies at really low temperatures, like, maybe 0 to 30 kelvins in a homework problem or something. Now he also said, though, that the molar heat capacity at constant pressure is roughly equal to molar heat capacity at constant volume, but both at P9. And that's roughly equal to AT cubed plus BT. And this is for metals. This also is true only at very low temperature. And B is a constant. And B is actually because of the conduction band electrons. So now what we have then is the same integral as before, but we're going to substitute in Debye's theory. So we have the integral molar at temperature naught is equal to 0 to T of Cp naught for the solid divided by temperature dt. So this is just the first integral that we had a problem with before. So this will be 0 to our low temperature, and that's going to Cp naught low over T, and then from T low back up to our temperature of fusion or whatever. So we split out this integral into two parts, the really low part and the rest of it. Now remember, SMT naught is going to be equal to integral 0 to T low. So that's going to be AT cubed over T dt, and that you pull out the A because it's a constant, and the T cubed over T obviously simplifies to T squared. And it's still the integral from 0 to T low of that T squared dt. So that just becomes A over 3 T cubed, and that's evaluated from 0 to our T low. So then we have the entropy molar at temperature naught and 1 bar is equal to A over 3 times the low temperature cubed, because obviously 0 cubed would be 0. And so that's equal to the Cp molar naught divided by 3 times temperature low. Okay, continuing on physical chemistry, chapter 5, section 7. So we have a graph here. Notice the units: heat capacity, constant pressure versus natural log of temperature. The dotted line shows this as an estimate for that formula we had, like maybe AT cubed or something. And then we have the curve for actual data points. If you integrate the area under the curve, starting at temperature equals 0, that's how you find absolute entropy. Now, if you don't have an actual formula, you have data points, then you use a method of numerical integration, such as the Simpson rule or Simpson method. The Simpson method says the area finding under the curve is basically the sum of all these different little boxes that you make really small from your data points. So you have your y values and your x values. So you're going to add your y of this data point plus 4 times y of the next data point plus y of the third data point divided by 6 and multiply by the width of your box, which would be x of the next data point minus x of the current data point. Now, we've talked about how you can't actually get to 0 kelvins, but you might be wondering how close you can get. Well, if you have liquid helium evaporating, kind of like a regular refrigerator, but with helium instead of ammonia or whatever, you can get down to about 1 Kelvin. If you have a paramagnetic sample, then you can use adiabatic demagnetization, and that'll get you down to about 20 nanokelvins. We'll be talking later on how adiabatic demagnetization works. That's an important process. If you use nuclear spin, then you can actually get down to about 2 times 10 to the negative 9th kelvins, so about 2 nanokelvins. Now notice the units of this graph versus this graph. It's the exact same information, but this is Cp against natural log of t. This is Cp over t against t. Now we're still doing the same thing. We're starting out with a dotted curve because we're estimating Cp is proportional to t cubed. And then we have actual data points all the way up to the liquid phase, and then we'll go all the way to the gaseous phase and keep going up. Integrating that curve, or this curve, will give us the absolute entropy versus temperature. So here, we start out with an estimate, we go up to solid, we have the temperature of melting or fusion. So there's an enthalpy of fusion here, that's why there's an increase in entropy here. Then you increase the entropy of the liquid as that heats up. Then you get to TBP, that's your boiling point, or your temperature of vaporization. This is not to scale, but this has actually a very large value because you're breaking the intermolecular bonds and spreading the molecules apart. And then you heat up the gas and the entropy continues to increase. So typically the entropy of vaporization is greater than the entropy of fusion. The delta S of vaporization, remember, is just the change in enthalpy of vaporization divided by temperature. And that's typically very large, but it's material specific. Continuing on physical chemistry, chapter 5, section 7. So we have all the stuff we learned before, combining it. Let's say we want the molar entropy of a gas at temperature 2. You remember, any substance is going to go through a solid phase, then a liquid phase, then get to the gaseous phase, presumably. I suppose some could sublime, but we're going to assume the liquid phase. So anyway, we're going to find the entropy molar at temperature 2 and standard pressure, which is 1 bar. So that's going to be Cpm over 3 naught, plus the integral from that lower temperature to the temperature of fusion, that's our melting point, of Cpm naught molar for the solid phase, divided by temperature with respect to T, plus the entropy of fusion divided by T of the melting point, or temperature of fusion. And then we're going to take the integral from the melting point to the boiling point of just Cpm of the liquid phase divided by temperature with respect to temperature. And then we're going to add in the heat of vaporization divided by the temperature at the boiling point, plus the integral from the temperature of the boiling point to our actual temperature of interest of the Cp molar naught of the gaseous phase divided by temperature with respect to T. Okay, now let's talk about the standard entropy of reaction. So we have the chemical reaction. It's going to be equal to the sum of all the parts. So we have delta S T naught T for temperature, of course. It's going to be the sum over all the substance I of nu sub I of the molar entropy at that temperature for substance I, and of course our standard 1 bar. And remember what we learned before, that nu I is greater than 0 for products and less than 0 for reactants. So what that tells us now is then the delta S of T2 minus delta S of T1 is just the integral from T1 to T2 of delta Cp naught over T dt. That's assuming no phase transition, obviously. This looks bigger because it had a couple phase transitions. And then, just like we already learned before, delta HT2 naught minus delta HT1 naught is equal to the integral from T1 to T2 of just delta Cp naught with respect to temperature. Coming up next is Physical Chemistry, Chapter 5. This here is all of Section 8, the standard Gibbs energy of reaction. So we know that the change in Gibbs energy at temperature and 1 bar is equal to the sum over I of nu sub I of the molar Gibbs free energy at that temperature substance I in 1 bar. Or put another way, the change in the Gibbs free energy at temperature in 1 bar is equal to the sum over I of nu sub I of the Gibbs formation energy at that temperature for substance I in 1 bar. Remember, F is for formation, not fusion. And then delta G at temperature in 1 bar is just H minus, you know what I mean. Delta G equals delta H minus T delta S. So even if it's 1 bar and a certain temperature, then you just write it as delta G at temperature in 1 bar equals delta H at temperature in 1 bar minus T delta S at temperature in 1 bar. And this is true at any temperature. It doesn't matter what phase or anything. This is physical chemistry. This is the end of chapter 5. This is all of this chapter 10 or section 10. This is the end of everything. Chapter 5, section 10. So we're estimating thermodynamic properties. What we're going to do is we're going to do it from the bond energies. For example, let's say we're going to go from this alcohol to this ketone. So you'll notice we're keeping these two methyl groups on the carbon, but we're going to get rid of this methyl group and replace this OH with a double bonded O. So we're going to take the reactants, we're going to break it down into separate atoms, and then we're going to create the products. Now we're going to break it down, all these bonds homolytically. What that means is that, remember, 1 bond has a pair of electrons. And so each 1 electron is going to go with the product, or each atom basically. Now, that's not necessarily the way it happens in real life, but this is how we're going to mathematically estimate it. Now, this is an estimate for several reasons, because, for example, we're going to say the bond energy of carbon-carbon is a certain value. These carbon-carbon bonds are probably not the exact same value as these carbon-carbon bonds because of the other stuff on it. But this is, like I said, an estimation. So what we're going to say is that any carbon-hydrogen bond is 415 kilojoules per mole. Any OH bond is 463 kilojoules per mole. Any carbon-carbon bond is 344 kilojoules per mole. Uh-oh. Okay, any carbon-oxygen bond is 350 kilojoules per mole. And any carbon double bonded oxygen bond is 750 kilojoules per mole. Now, the change in enthalpy of the reaction, remember, we're going to add up all the bonds broken that we broke here from the reactants, or whatever you want to call it. And then we're going to subtract out the sum of all the bonds formed in our product over here. So what we did was we broke 7 CH bonds, 2 carbon-carbon bonds, 1 carbon-oxygen bond, and 1 OH bond. And we're going to subtract out 6 CH bonds and 2 CC bonds and 1 CO bond. Now just to make the math easier, you can simplify that first. So that cancels out and you get just 1 CH bond, 1 CO bond, and 1 OH bond broken. And then we created just 1 C double bonded O. You probably could have figured that out yourself by looking at it, but it's good to do out the process a few times to make sure. So then we put in the values. So we add up 415 kilojoules per mole, plus 350 kilojoules per mole, plus 463 kilojoules per mole. Subtract out that 750 kilojoules per mole. So going from here to here, the change in the enthalpy is 503 kilojoules per mole. That's the end of chapter 5.